Alright, so today we're going to start talking about the absolute value function. You may remember that absolute value talks about the distance away from zero. Like how far is this number away from zero? So your result is always going to be a positive value. So like the absolute value of 4 is 4. It is 4 units away from zero. The absolute value of negative 2 is positive 2 because the distance from 0 is 2 units. So we're going to focus on the graphs of absolute functions today. And in order to do that, let's just substitute in some x values and see what y values we get, and then go ahead and plot those. So we want to have some negative and positive numbers in our graph. So let's do x equals negative 2, negative 1, 0, 1, 2. Now the absolute value of negative 2 is positive 2. The absolute value of negative 1 is positive 1. The absolute value of 0 is 0. Absolute value is 1, of 1 is 1, and the absolute value of 2 is 2. So now if we plot those, and x is negative 2, y is positive 2, negative 1 comma positive 1, 0, 0, 1, 1, and 2, comma 2. So if we were to connect this, this looks like a V. Now all absolute value functions will be V-shaped, and they have something called a vertex, and that's the pointy part. So the vertex is the pointy part, and it's at 0, 0 in this graph. This is the vertex. Now you notice that it's two lines here. We have this line that has a negative slope and this line that is a positive slope. So the purple one has a slope of negative 1, down 1, right 1. And the red line has a slope of positive 1, up 1, and right 1. And this graph opens upwards, so up. Domain and range, the domain is the x values. We can substitute in any x value we want. So our domain is negative infinity, comma infinity, or all real numbers, which is this symbol. You could use either one. But the y values for this particular graph, the smallest y value we have is 0. And we use the bracket because 0 is included. We always use a parenthesis with infinity. So the y value is the smallest one we have is 0, goes all the way up to infinity, and 0 is included, so we have that bracket. This bracket means included. The parenthesis is not included. And we're going to talk about domain and range more a little bit later. Now the general form of an absolute value function is y equals a times the absolute value of x minus h, and then plus k on the outside of the absolute value. So let's explore what these do. So we have another function, and it's a lot more complicated than f of x equals the absolute value of x. We have y equals negative 2 times the absolute value of x plus 1 plus 3. So let's use those same x values we did above, negative 2, negative 1, 0, 1, 2. Now the y values, let's substitute these in. Substitute negative 2 in for x. Negative 2 plus 1 is negative 1. The absolute value of negative 1 is positive 1 times negative 2 is negative 2 plus 3 is 1. Then negative 1 plus 1 is 0. Absolute value is 0 times negative 2 is 0 plus 3 is 3. Now 0 plus 1 is 1. The absolute value of 1 is 1 times negative 2 is negative 2. Negative 2 plus 3 is positive 1. Then we have positive 1 1 plus 1 is 2. 2 times negative 2 is negative 4. Negative 4 plus 3 is negative 1. And then 2. 2 plus 1 is 3. Absolute value of 3 is 3. Times negative 2 is negative 6. Plus 3 is negative 3. Now that maybe got a little bit confusing because we had to do a lot of stuff in our head and did some mental math with the absolute value, then multiplying. So we're going to talk about some easier ways in a minute to graph these. So let's plot these points now. So we have negative 2, comma negative 1, positive 1, negative 1, comma positive 3, 0, comma 1, 1, comma negative 1, and 2, comma negative 3. So this graph looks like this. So let's focus on this a value first. That's what we have here. This a value, our a value is negative 2. So notice the difference in this graph compared to our mother function up here. This one is opened upwards. This graph is opened downwards. So if a is negative or less than 0, then there's going to be a reflection over the x-axis. When a is negative, that's what we call a reflection over the x-axis. If the absolute value of a is bigger than 1, we call that a vertical stretch. Notice how that graph is stretched out a little bit. If the absolute value of a is less than 1, then there's a vertical shrink. Vertical shrink. And then a helps determine, I call it the slope of each part of the v. Because look at the slope of each of these lines. Up 2, right 2. Right 1. And then from here, down 2 and right 1, down 2 and right 1, negative 2. So that a value helps you with the slope of our graph. Then the effects of h of k. So let's go back here. What's the vertex? The vertex is the pointy part right here. That is negative 1, comma positive 3. So if we compare that to this function here, where do we see that? Well, 3 and positive 3, that's easy. But it says plus 1, positive 1, but our vertex is at negative 1. So it's going to be the opposite of what we see to get the x-coordinate of the vertex, but then our y-coordinate of the vertex is going to be exactly what we see. So let's write that down. H is the opposite of what you see, and k is exactly what we see. So what that means, when we add number on the outside, so we added 3 on the outside of the absolute value, we moved up. Well, if we subtract, I think we can deduce that we go down. So outside numbers are very easy, but now when we add or subtract number on the inside, it moves in the opposite direction of what we would think. So if we add a number on the inside, okay, up here we were adding plus 1, but our vertex is negative 1. It moved left 1 unit from 0, 0. So the graph moves left, and if we subtract a number on the inside, the graph moves right. So we're going to use this information to help graph a little bit easier and not have to require a table. Because what if your vertex doesn't show on a table? Then you're going to be having to guess more points. So for the following example, we're going to graph this, and we're going to compare this new graph to the parent function from this first page. So let's identify our vertex, opposite of what we see, so negative 2, comma, exactly what we see, negative 4. So that's our vertex, negative 2, 1, 2, then down for 1, 2, 3, 4. Okay, there's our vertex. Now if we go back up here, our a value tells us the slope of each part of the v. Here we didn't have a number in front, we had an invisible 1. And we went up 1 and left 1, and then up 1 from the vertex and right 1. So our a value is an invisible 1 here. So from the vertex, we're going to go up 1 and left 1. Up 1 and left 1. And you don't have to do this many dots. And up 1 and right 1. Up 1 and right 1. So we were able to graph it without creating a table or anything like that. Now the transformations, or comparing. Whenever I ask you to compare, there are three things. R, S, T. R stands for a reflection. Is there a reflection in this graph? Well, how do you tell? Up here, if a is less than 0 or a is negative, we have a reflection. Well, we don't, our a value is positive 1, so there is no reflection. We need to write none. Don't leave it blank, write that there is no reflection. Shrink or stretch. Well, how do we know there's a shrink or stretch? Again, a, if a is greater than 1, if the absolute value of a is greater than 1, then it's a vertical stretch. If it's less than 1, then it's a shrink. Well, if it is equal to 1, there is no shrink or stretch, so none. And then translation, how did our vertex move from 0, 0? We went left 2 and down 4. So that's all we have to do when it comes to graphing absolute value functions. All right, so I want to summarize this RST stuff down here. So again, we have a reflection over the x-axis if a is less than 0, which means a is negative. We have a vertical stretch if the absolute value of a is greater than 1. So what I like to say is if the numeral in front, ignore the sign, ignore the positive and negative sign, if the numeral in front is bigger than 1, then you have a vertical stretch. If that numeral is less than 1, we have a shrink. Okay, then a translation. A translation goes left or right, h units, and up or down, k units. So now let's graph these problems. Alright, so the first thing we're going to do, we have y equals 1/2, absolute value of x plus 2 minus 3. Our vertex is the opposite of what we see inside, so negative 2, comma, exactly what we see, negative 3. So negative 2, 1, 2, down 3. Now, the a value, a is equal to 1/2. So from the vertex, we're going to go up 1 and right 2, because 1 over 2, rise over run, up 1, right 2, and it's going to look like this. Then we go from the vertex up 1 and left 2, and it looks like that. Okay. Now, is there a reflection? No, there's no negative in front, so there is no reflection. Shrink or stretch. 1/2 is smaller than 1, so that there is a vertical shrink. So vertical shrink. Translation. Our vertex went left 2 and down 3. And there is our graphed absolute value function with all the required information. All right, now let's try this one. Our vertex is going to be at +1, comma, +2. And our a value is -3. So from our vertex, we can go down 3 and right 1. Down 3 and right 1. For our vertex, we're also going to go down 1, 2, 3 and left 1. 1, 2, 3, left 1. RST. R stands for reflection. A is negative, so there is a reflection over the x-axis. Stretch. There is a vertical stretch because 3 is bigger than 1. Okay, because remember, we're taking the absolute value of A. That tells us if there's a vertical shrink or stretch. And then our translation, we went right 1 and up 2. So some of this may have been a little bit of a review for you. Others, it may have clarified some things you learned previously. So hopefully we're able to graph these absolute value functions. They're really not that bad once you break it down into each of these steps. So thanks for watching. Make sure to like and subscribe.